Hi, everybody. Today we're going to continue on our critical thinking, and we're going to talk about hallucinations and language models. In particular, we're going to go over their mathematical inevitability, at least according to OpenAI now, from this paper. And we're going to discuss very briefly why this is being shared now, as opposed to 3 years ago, maybe. And then lastly, given this new information, are language models useless? Discuss this question. All right, so as far as the inevitability goes, OpenAI produced this paper about a month ago. I've just been crazy busy, but I've been meaning to talk about this for a while. Oh, sorry, OpenAI and Georgia Tech. And the short of it is they basically explain, I just have skimmed this, that hallucinations are inevitable, even if you train on perfect data. And the idea, essentially, well, the way they describe it is that they're more rewarded for giving answers than giving no answer, even if the answer they give is incorrect. I think that that's not exactly the crux of it. I would argue that principally what's going on is it's the stochasticity that we talked about before. If we look at our language models, they have stochasticity built into it, and hallucinations are a byproduct of that stochasticity. If language models were not stochastic, then if they were deterministic and they gave the wrong answer, what you would do is, or at least what I would do, is when they give the wrong answer, you then use a reinforcement algorithm to say, that's the wrong answer, try again. And then they would try to come up with a different answer, and eventually they would get it right. And you say, that's the right answer, stick with that. And then what would happen is eventually it would just only have the correct answers. You would eventually converge on all the correct answers, and that's principally via determinism. So this paper and the news articles around it, like this one, personally, I'm not surprised by this at all. This is something that I've believed, and while I don't know that I've had time to try to actually prove this, it's very easy to demonstrate, but to actually walk through and give the proof, I don't know that I've done that before. But even in the class that I teach at the university, I'll describe the various ways that neural networks are stochastic. And yeah, so I think we've discussed this on the channel, but as a quick refresher, there's minimally like 3 ways. The initialization of the weights tend to require to be stochastic, otherwise you lose certain convergence properties. So if you don't randomly initialize them, then you can very easily get stuck in spaces where the models don't converge to an answer, which you don't want. The second is when you do the training of large language models, you tend to use techniques that don't serialize the training because you want it to run as concurrently as possible to sort of minimize the serialization points, like from Amdahl's law, right? And because of that, that introduces stochasticity in the training, which makes model generation not perfectly repeatable. Even if you have the same percentages for that, you just have the same numbers for all the outputs. The underlying model might be different, and that results in like multiple variants of the same model when trained on identical data. That's the second form of stochasticity. And then the third is that there are variants that actually exist in the environment that will cause differences of training execution that are outside of those two. So even if you had the weights initialized all to the same value and somehow that worked, and you had a specific serial order of training across the entire cluster of machines that you're training the language model on. So you assume that you get those locked in serially. The jitter, or the sort of the perturbations in the actual computing environment, also cause non-deterministic execution of training. So like a simple example of this is you may have programs that are running co-residently, and that slows something down. Or maybe you're using a framework that has garbage collection, and the garbage collection kicks in at a random time in different executions. And so then it trains the order of the training, right? So generally those three things minimally all introduce elements of stochasticity for the training. But it should be like fairly obvious, I think, just by using these systems that they are stochastic. And then for people that are actually developing with them, like we are at Merly or others are, that stochasticity likely jumps out immediately when you're doing things like what we were talking about last time, which is you're trying to do iterative refinement on the software engineering. So the stuff right around here, and you like very simple example is you have the word strawberry, right? And you ask the system, this was like a real bug, I think, at some point, how many R's are in strawberry? And it's sort of like, it says 2. And your users are saying, oh, it's having this stochasticity error. It's actually 3, right? And so you then bring this internally and test it. And then the first thing you get with a stochastic system is it gives you the answer 3. So then from your lens, you're like, oh, it's actually correct. There's no bug here. But again, that's one of the core challenges with stochastic systems is it's stochastically correct here. And in the other case, it's stochastically incorrect. So anyway, let's say that you then eventually can get the answer 2. And so you're like, okay, cool. Now I'm going to try to fix this. And you make changes, and it does change this to 3, at least in this attempt. So from here, you can go in all kinds of wacky directions. Like you can say, actually, that was just a stochastic execution. And then when you run it again, it gives you the answer 2 again. So it's not actually fixed. Or you can have this other branching condition where actually it is fixed and it's 3 now every time, but you broke 10 other things over here that were correct before. So, or problems that are in a very similar vein also don't work. So like pineapple, how many peas are in pineapple, or something like that. And this is, in my mind, the real crux of the problem, in that having AI systems that have stochastic elements to them, I think, are fantastic in certain spaces when you want stochasticity. Like, for example, let's say you don't know where you want to go eat dinner tonight. And so you give the AI parameters and say, I want something that is within this price range, in this city, something like that. And you want those parameters to be fixed. So you don't want those to have variation on them. So let's say dinner in Palo Alto between the hours of 5 and 7 p.m. for 2 people. Now, you do not want stochasticity in those parameters, right? Because then, like, why are you giving them the parameters? Or maybe you want a small amount, like, oh, well, it's not actually in Palo Alto, it's in Menlo Park, but it is close enough, right? Okay, maybe. But the actual selection of the restaurant, you may want that to be stochastic. that actually may be great. You want to be surprised. You don't want necessarily a fixed list. You want to sort of throw dart at the dartboard. And in fact, a lot of people, as I understand it, I'm not really big into this, but I think a lot of people enjoy sort of the surprise and the unpredictable nature of games, right? And certain games have more variation, and I think you can lose a lot of money this way. You can maybe get lucky and win money, but the point is that having some amount of randomness when it's controlled can be really good. Uh, but it's really important that we are genuine about these issues. And so when, you know, part of the reason why we built, again, Mentor the way that we built it, and we've made the decisions at Merle the way we have in terms of the AI that we use foundationally, is that we won't use stochastic machine learning systems at the foundation. We will use them as auxiliary pieces that can leverage the stochasticity of language models. And in particular, Mentor is, I think, my personal view is that uh, the way Mentor works for the stochasticity of language models in code generation is probably maybe like a very simple but like reasonable example of how one might want to do this. So let's just pick something. Okay, we'll pick my friends over at Snorkel. Love those guys. Actually, worked very closely with their founder and CEO, Alex Ratner, for some time. It looks like maybe Mentor is running slow today. Okay, there we go. So we'll click in here and we'll just pick, I don't know, whatever this is. All right, so Mentor is deterministic in the way that it detects issues. So it's still fully learned. So it's trained on like 1 trillion lines of code. And we're essentially leveraging, I think, the power of machine learning to reason about a lot of data. But then after the system has been trained, the results on the issue detection is deterministic. And what I mean by this is that if you download Mentor and then you add this Snorkel repo on your machine or in the cloud or whatever, and you run inference the same way that we did, you will get exactly the same answers. Not just like close to the same answers, not approximately. It will be identical as far as the issues that it finds and the score that it gives and all of this stuff. There'll be no variation. It will function like a calculator. In that when you say 1 + 1, it gives you 2 every single time, not just 99% of the time. And from my view, again, as we've discussed many times, hard science, I think, tends to be more deterministic. And it's often the case that you want that determinism because that's the foundation of your house. Now, sometimes, though, after you get beyond the foundation and you get higher up, you want a little like creativity. You want to brainstorm. You want to look at a bunch of different options, right? So again, let's take the dinner example. You and your friend, your partner, whatever, are going to go to dinner, and you know that the constraints have to be between 5 and 7 p.m., and you know you want it to be in Palo Alto, but nobody really has a preference for food. That's great. And so basically in that case, it's like, as long as it's a restaurant and it's open, that they can seat you and it's in Palo Alto, it's going to be basically a correct answer, even though it's fully stochastic. And so my view is this is also valuable for code gen, is that for code generation, I would argue that generating potentially multiple solutions for a problem like we do here can be valuable. And part of that is that I think for the coders out there, especially the ones that are very seasoned, you are likely deeply aware that I can solve this problem 300 different ways. And each solution has various different trade-offs. And so what do I want here? Do I want something that is super fast, but it's very hard to read? The code's going to be like super obfuscated, and 3 people on the planet are going to understand it. Or do I want something that's very easy to understand? It's going to be super maintainable, but it might be slower, right? Oftentimes slower code is the better choice, which may sound a bit strange, but not all code needs to be fast. That there's like the was it like the 80-20 rule is 80% of the performance degradation or bottlenecks is maybe 20% of the code. Maybe it's more like 90-10, right? And so a lot of times you want code that is actually going to be more readable, maintainable, modular, all that stuff, over code that is highly performant. Why? Because code that tends to be extremely performant is oftentimes, it can be, it's often more complicated. And because of that additional complication, it can be more difficult to understand, to maintain all of this stuff. Anyway, so going back to the stochasticity part, is this is why Mentor has a bunch of different answers, is that it's basically saying, okay, so you have this piece of code. I'm going to write it this way. That's one potential solution. I'm going to write it this way. And I'm going to write it this way. And then I'm going to write it this way. And just quickly looking at that, I can see that those answers are maybe not all identical, but it's very possible that those answers are actually all correct, very much like the restaurant example. Is as long as it's within those parameters, that's a valid answer to the restaurant question. And you likely want that because it might be boring. It might be just that you don't learn things if it's always giving you the same sort of pizza. It's always pizza. It's always Tony's pizza. And then you and your friends or your partners like, okay, I want something other than Tony's pizza, right? So having that stochasticity, I think, can be very valuable for those types of problems. And even in problems that are hard science, which I think writing software is, mostly, not all aspects, but a lot of software development is hard science. There are soft science elements to it. And this is potentially one example, is that while in this case, what we're doing is we're looking at 4 different answers, and all of these may be correct from a very objective perspective, in that the way to show correctness is given an input, executing some code with that input gives you a specific output or state. And let's say that that output and state is correct. Then, given that input to another piece of code that's different, if it gives you the identical state and output, in theory, that code may be correct. And then you just go. And so potentially it could be 100, 1,000, whatever, different answers to this problem that, as long as it satisfies those post conditions, then it's like, yeah, who's to say that this is wrong? And then it becomes a question of taste or subjectivity, or what matters in this context, right? Like maybe you're working in the classified sector and you need to make sure the code is very secure. Oftentimes, code that is very, very secure is slower. Why? Because you tend to have to do like additional security checks and things of that nature. So software in software development, we're often having to deal with things like trade-offs. There tends to not be a panacea where this one solution gives us the answer to everything. Let's always use that. If that were the case, then there would probably be one programming language and one sort algorithm or something like that, right? Which is not what we see. So the point of this little detour is that I'm of the view that language models having hallucinations, or I think a more honest, because I don't know, like I still don't totally love this word. In the research papers that I review and work on, sometimes people are calling it like confabulations now. Okay, I mean basically what it is it's an error that is derived from stochasticity. It's it's an error that's derived from stochasticity, and so if we want to give it this fancy name like hallucination, whatever, uh, it seems weird because I think we usually refer to things that like are alive, like humans, animate things, organic matter, I guess, that have these hallucinations. And so I think it might be not setting up the best precedents. Like people are already thinking that these machine learning systems are alive and they're conscious and whatever. And as a scientist, I've seen no evidence of that. And again, one of the best ways to demonstrate this is just take the computer where the model exists and just turn the power off and then turn the power back on, and then it still works, right? That would be equivalent to if it were a human, uh, unalive the human and then alive the human and then see if they do all the same stuff. So like you can't do that with humans, right? It's like you can't hit the power button and then turn the power back on and then everything works. So what does that tell us? They're not alive. I mean, I it's very strange. Like I think it can be reasoned away in a very simple way, but I think the people that are sometimes arguing this, one of my favorite quotes is you can't reason people out of a position that they didn't reason themselves into. This would be an example. Is the people that got there to the I think this thing is alive, like how did you get to that conclusion? Well, not through evidence, because the evidence is yeah, it's sort of you're making a lot of potentially dangerous assumptions. Anyway, the point of all of this, I guess, before I get too sidetracked, is this stochasticity can be useful in many ways, in my mind, uh, but it's very disingenuous to people that are trying to build systems that rely on these when companies, organizations, institutions, whatever, are saying things which has very much been said in the past. In one of the loudest voices I think was from OpenAI and Sam Altman saying that it's just an engineering problem. We'll just engineer it away. It's like that. That's like saying that you can somehow engineer away the fact that when you divide by zero, it's unknown. Like no, you can't engineer that away. That's a fundamental property of the number system. And we need the number zero, but there is no way to describe what it means to divide something by zero. It has essentially no meaning. And so you can't engineer that away. It's always going to be undefined. You can give an answer and say it's undefined. You can say this is not a number, but you can't suddenly say, yeah, we're going to work on this, and then now it's 5. Number divided by 0, the answer is now 5. Like we've got it. That's not going to happen. And same thing with this this hallucination thing. Is if you understand things foundationally, like really deeply on not just like use the frameworks to generate a model, but you understand the core principles of machine learning, like we were just talking about with the stochasticity. If the system has inherent stochasticity that cannot be elided away, there is no way that you can remove the hallucinations. That's what's causing them. And this is very important because this is not related to all machine learning. There are many machine learning things that are also probabilistic, but they are deterministic. And so if we go down this rabbit hole just a little bit, when we, me and my graphs, let's say we have a system that's probabilistic, and then we'll call it stochastic, this S. So what you want over here, let's say that this is the best quadrant, is you maybe want a system that is probabilistic, but it is not stochastic. And then so over here, let's say, we'll just say up here, this is all the space of ML, and down here, this is like the space of not ML, something like that. I'm just flying by the seat of my pants, so I'm probably not going to get this perfectly correct. So this is probabilistic and this is stochastic. So this is like, things like language models. And over here, it's probabilistic and not stochastic. This is things like Merle's AI. And so up here, this is all the probabilistic stuff. And so down here, this is not probabilistic and it's stochastic. And then down here, this is not probabilistic and it is not stochastic. And so these would be things like something that's not probabilistic and not stochastic is just, we'll say, normal PL code, just like hello world type of stuff. Most of the programming languages, when you're not using something like Rand, it's not probabilistic and it is not stochastic. So essentially instructions, let's say you have a range of instructions 1 through 10, you're going to execute 1 through 10 unless there's some sort of error, right? But the point is that that's neither probabilistic nor stochastic. And then something that is not probabilistic, but it is stochastic, I guess maybe I'm probably not exactly right on this. So feel free to correct me in the comments. This would be like a pseudo random number generator. So as I think many of you know, most of the number generators that we use today, like in Rand, they're not real random number generators because like true randomness is that happens sort of in nature, as I understand it, is extremely hard to do correctly. So instead, what the pseudo random number generators are is they're actually a fixed algorithm that will find we will return sort of numbers in a range, and the way that so it will be this sort of stochastic thing in the sense that you won't know exactly what you're getting, but that stochasticity is based basically on this seed. And so this seed, if it's fixed, it's not stochastic. It's always the same. But if the seed changes, then it's stochastic. And so maybe this is an example of, like, again, I'm just sort of spitballing here, that this is something that maybe it's not probabilistic, but it is stochastic. And not probabilistic in the sense that I think it already knows essentially the concrete items or the way that the items will be generated. Whereas a true probabilistic system, what it will do is it will sample data. It has data that exists in the wild, and it will sample some of that data. And then from that data, it will then try to give you answers that are probabilistically based off of the sample data that it's trained on. And the sample that I'm talking about here is usually like the entire training data set. But keep in mind the training data set, the reason why we call this a sample is that whatever the area is that you're working in, more likely than not, the data that you're training on is not all the data that exists in the world. It's some sample of all the data that exists in the world. So your data may be complete. So you may be saying, oh, I don't sample the data, I use the whole data set. Sure. Uh, but there's much more of that data. Like, for example, if you're learning how to identify dogs in photos. So you've got this training set. So you don't sample that training set. You just use the full data. Yes, but there are more pictures of dogs in the world that you don't have. Minimally, you don't have the photos of my dog. So there you go. There's your proof. Anyway, what's really important to understand here is not really the space here, right? This is sort of how we've done things for a very long time. And we love the space. We use the space. And this is the stuff that we use sort of foundationally. But what we're talking about here is that there's ways to do machine learning that are stochastic and not stochastic. But they're both still probabilistic. And so I guess the key idea that I'm trying to get across is, to the best of my knowledge, all machine learning methods are probabilistic in nature. That's why they're learned. If they weren't probabilistic, you would know essentially the algorithm a priori. And that's what you're trying to learn. You're trying to learn essentially. So there's like the two types of actually, yeah, I'll just bring this up. Essentially, two types of I think it's right over here. There's these sort of two ways of building these algorithms, just in general. You can do rules-based or you can do stats-based. These are sort of the only two ways that I know that we can build algorithms today. And the rules-based, one way to think about this is the rules-based, this is still based on data. It's just data that humans have. It's our knowledge. And so the rules come from all the observations that we've made from that data. So this is from human knowledge, and this is this is essentially the human data that we have formulating the rules, and this is the machine data, and it trying to extrapolate the algorithm from that lens. So I'm not explaining this, I think, too well, but rather than thinking about it in a like stats based and rules based, which is sort of what it is, you can also think of it as like human learned, machine learned. Both are still learned. It's just the rules based one we already know, so we know the algorithm. The stats based one, we don't know the rules, we don't know the algorithm, and so we're sending the machine out essentially to go figure that out. This is maybe like a more meta way to think about this that I actually kind of like, because I was talking with Paul about this a couple days ago, and one of the key things that I think we're missing with many of the advances in neural networks today is that they're not interpretable, they're not understandable, and that's a problem if we are trying to level up science at the same time that we're getting answers. So it's like, it's great that we're being able to build products that have value, but it would be even greater if we could build those products to have value based on all this cool ML stuff, but then have those systems be understandable and interpretable. So the rules that it's learning, essentially, like what are the rules that you have for figuring out that this is a picture of a dog? you could be explained potentially to humans, and then we could write the rules based. And part of the reason why this is preferred in some sense, or one of the reasons why you might have preference over rules based than stats based, is that then when there's a bug, you can just tweak the rule slightly because the rules are all understandable. Like we wrote the rules, so we understand them and we can modify them. When it's stats based, it's just sort of like, well, often is the case. We just have a whole bunch of stuff. And so it works. And when it doesn't work, it's sort of like, but I don't know why. I can't just change one line of code. Anyway, so I'm really getting a little bit of a detour here, but what we're really trying to point out, higher order bit I'm trying to tease out here, is you don't need to have stochasticity in the underlying algorithm for machine learning. And so it's important to not overgeneralize here. Like what I think Computer World may have accidentally done with the title of this. It's not that all AI systems have hallucinations. It's that language models do. And I do think that the authors of OpenAI and Georgia Tech got the name right. It's language models that hallucinate. It's not, logistic regression, linear regression. The Merle AI, these things, they don't have the stochasticity, therefore they don't hallucinate. I also want to point something out that is very, I think, critical to this is I really like the way that they called this just language models. It has nothing to do necessarily with the size. So small language models will likely still have this. Large language models, any kind of language model. Essentially, what we're really getting to is that it's a neural network problem. The problem is the architecture, the underlying architecture of neural networks. Now, again, I'm not saying don't use neural networks, use them. But in cases where you cannot tolerate hallucinations or errors, in cases where you need fully deterministic trusted behavior, and that determinism can be wrong, but you can fix it, then you just generally are not going to want to use neural networks because it's not the right. Like, for example, if I were to tell you that you need to write a program that's going to do something, but it needs to follow real-time constraints for certain operations, and then you come back and say, okay, sounds great, we're going to implement the system in Java. I would say you've already failed. And like, why? Well, Java has garbage collection. Garbage collection is non-deterministic and therefore can't necessarily be guaranteed to provide real-time constraints. So it doesn't work. You can't use it for that problem. That's why people don't build real-time systems, at least to my knowledge, in Java, unless it's a Java that has a deterministic garbage collector, which I think maybe some people were working on. So maybe that's work in progress, but hopefully this gets to the point that let's not overgeneralize here. Let's talk specifically. This one is pretty good. It's a language model problem. It's really a neural network problem, and other AI systems don't have this issue. Specifically, the ones that are not stochastic. All right. So I think we've sort of beaten point one to be unalived, and so we're done there. The next question I think people might naturally have, and I certainly have, is why now? Why write this paper now? Why make it public? Look, I even have OpenAI's talk about it. It's directly on their website. They're making it very clear that this isn't just a paper that they wrote. This is a moving forward, it's very important that everybody know our systems are going to have hallucinations. So why say this now? It's my strong conviction that for a long time, OpenAI and other hypey AI companies were looking at things in, like, I think a positive way. I think I like the positivity that people have on the hope of being able to get rid of certain problems. Like we're not sure how we'll fix this, but we'll figure it out, right? I love that mentality. But I think it's also important to check yourself so you understand what the constraints are, so you don't sort of go down the path of trying to solve the problem that cannot be solved. Like there's no way to solve this. For example, I can't magically sprout wings, and I can't say to someone, I'll figure it out. I don't know how to do it, but I'm going to figure it out. And so I just, like, that's sort of outside of the realm of at least the world that I live in terms of rationality. So this raises a couple additional questions in my mind. And I think it kind of goes down to maybe like two general directions of the questions. The first, in terms of like why now, is the direction of OpenAI truthfully did not understand machine learning deeply enough to realize that hallucinations are inherent to neural networks. That's option one. And option two is they were fully aware, but they sort of needed to win trust, or they needed to get market share, or they needed something to incentivize people to use their stuff with the belief that this is just like, oh, it's just growing pains. Eventually this will be solved. Now, I'm not the knower of all things. By the way, there's other possibilities too. I think these are just maybe the two most obvious. I'm not the knower of all things, so I don't know which one it was or if it was something else. But what I can tell you is that from my perspective, as someone that teaches neural network architecture and has some degree of understanding, which could very well be significantly dwarfed by the experts at OpenAI. I mean, who knows? Or at Meta. Like, does Jan LeCun know more than I do? For sure, right? So if that's the case, if they have these super geniuses that know significantly more than I do about this, that would kind of be lied away option one, right? Option one would be like, well, no, they did know, because they have all this knowledge and they're building these really big things. So then that leaves us with option two. Option two is that they knew it, but they just didn't say anything. And then why now? Why not just keep this a secret for forever? I think the answer is right there. I think it's GPT-5. I think that with the release of GPT-5 and the lukewarm performance, performed a little bit better in some areas, performed worse in others, I think the realization is this whole step of adaptation is hyper unreliable now, and they realize there is no engineering way around it. No matter how much money you throw at it, it's just not going to make like me sprout wings or neural networks stop hallucinating. And they finally have to sort of come clean. Otherwise, I think that people are going to just stop using their stuff because they're going to continue to overpromise and underdeliver and burn a lot of trust. This is my speculation. I think that they absolutely knew for a long time and really didn't tell anyone. And I think that that is unfortunate because what I think happened, and I've experienced this firsthand when we were at various points raising money at Merly before where we are today, a lot of the investors would ask questions like, why is the whole system not based on language models? And I would try to explain to them this problem. Say, well, we kind of work in the space of hard science and we need our system to be reliable and give you these deterministic answers so we can move the software forward in terms of its quality. And language models, while really cool, awesome, shiny new toy and do really awesome things with their, what I tend to refer to as spherically constrained stochasticity. We'll maybe get into this at some point. So this is, by the way, this is a new term that I think it's not exactly right. So spherically constrained stochasticity, SCS. But I think what it really is more of like it's like a manifold constrained stochasticity or a geometrically constrained stochasticity. We're still trying to figure out exactly how what term to use here because this is all sort of bleeding edge science, right? But anyway, spherically constrained stochasticity is this notion that the answers that you get from these systems are like a bullseye, and dead center is correct. I think we've spoken about this before, but just as a quick refresher. And then everything outside of that bullseye is degrees of incorrect. And what you want to do is have the smallest sphere as possible in terms of things that are related to hard science. And if that's the case, then it just sort of can't be stochastic. It has to be deterministic. So anyway, I would explain this with VCs, or I would try to. And some of the folks that I would talk to, the technical experts that would do diligence, these are like PhDs from Berkeley and Stanford, MIT, all these like fancy places. And I would try to explain it to them, and they'd be like, "Oh, you just don't understand language models." And yeah, possibly. I mean, that's certainly a possibility. But I think it's also possible that the world historically was in a little bit of a bubble, and people were. There's a lot of the blind leading the blind. And I think that we're moving beyond that now. And thank goodness, I wish they would have done this sooner for a variety of reasons. One, I think there's a bunch of investors. Like, I don't think that all venture capitalists are bad people. I think that many of them are really great people and they want to do good things and they want to help companies grow and also get a return on their money. And a lot of them, I think, were hoodwinked because people were not telling the truth about language models, or people were, and they just weren't listening because my voice is too tiny. Which part of the reason why we created GTT is to try to just spread the word and try to help set the community on technology so people understand at least what we believe, what is true, what is false. It's sort of the relationship that I have with MIT Tech Report is I have a pretty strong relationship with them. They'll come to me and say, Goju, what is hype and what is real? And then I'll try my best to explain to them as they've covered in several articles. And oftentimes when I'm doing this, I will unfortunately be the outsider voice that's disagreeing with a lot of the incumbents because I think some of them, at least historically, up until now, were saying things like, oh no, the language model hallucination is just an engineering problem. Yeah, no, like I think it's provably not. It's an inherent characteristic to the fundamental design and architecture of neural networks. Okay, so that's maybe the second point. This maybe the why now. And whatever the reason is, the view that I have is this is good. one, I'm a strong proponent of just telling the truth. And so I'm really glad that OpenAI is telling the truth, because now I think all the people that like weren't listening to the people that were being honest about this, they were looking to OpenAI for whatever reason. Well, now OpenAI, I think, is finally being truthful, and we can stop with the flat earther thing. We can stop with the emperor's new clothes. We can stop pretending and move back into the world of reality. So get us out of this, the Gartner hype cycle. It's like, it's, it's like, this is a really bad. Oh, let me try this again. It's more like this. And so this is like this is maximum hype. And this is something like excitement. Yeah, yeah, something like that. Excitement. And this is, I think, knowledge. Yeah. And so when you first get these new things, like the lack of knowledge, or, I think there's also time passing forward, but they're sort of intertwined. Anyway, this is the maximum height point. And then there's this, is it like the trough of disillusionment or something? Disillusionment. And then this is basically, it has value. It has value, and people have learned how to think again. So this is rationality, and I'm huge on rationality. I'm really big on just us using our brains and not using our emotions to drive us in really important decisions. Because just because you're mad right now doesn't mean you burn everything to the ground, right? Emotions are fleeting, whereas rationality is sort of, let's think about the bigger picture. And so this max hype is sort of like max emotion. We'll call it max irrationality. So we were, I think, over in this space, and now I think, like, I mean, maybe you guys can comment and share what you think, but I think that we are now, I think we're, if I had to speculate, I think we're around here-ish, because things are going down in the excitement and the irrationality, which I love, because now, because I am a very strong proponent of machine learning, or AI, as I guess we call it today. There's still some debate, again, if it actually is intelligent. But I think it's not debatable on whether the machine is learning, which is why in the scientific community, we can tend to call it machine learning, not AI. Anyway, I think that we're probably around here. And I think that's great, because this is diffusing the hype. It's bringing people back to reality, and we can properly assess what the capabilities are and get out of this mode of magic happens, right? That's sort of the view that we had before, or the community had, where it's like, oh, it's just an engineering problem, right? Oh, it's just, well, magic will happen and fix this. It's no, that it's science, and there are trade-offs, and you have run into a trade-off, and let's just be real about that. Okay, so that gets us through maybe the first 2 points, and I love it. I love that OpenAI has come clean about its inevitability. I love that the rest of the world is actually seeing this at like this global level, and I do not think that this takes away from language models or AI in general. I think all it does is it is helping properly set expectations, and it's more clearly explaining where these things should be used, which gets us to our third question about, are language models useless? And if it's not clear already, I would argue that they absolutely are not useless. They are very useful in the right context. And so this is one where I think that they are useful. I think almost any space where you are in an area where it's more subjective or open for interpretation. You can even use them foundationally. But if you're working in a space like Mentor is, or you're working in a space that's hard science, so you're a chemist, or you're an aerospace engineer, or you're in the financial sector, stuff where you need to have deterministic, objective outcomes or output, the use of language models in that space is probably going to be less. It's not elided entirely. It's just going to be not as prolific because a lot of these hard science spaces need strong guarantees on the determinism, whereas things that are more subjective, like let's just write a little bit of this down. I don't know, poetry, uh, music, art, movies, and so on and so forth. Food, right? A lot of these things they have wide degrees of variance in terms of what is acceptable, what is the best. There's no 1+1 is 2 type of situation. And so right out of the gate in those spaces, I think that language models are fantastic. And I think if you think about the fact that language models are stochastic machines, if you think about other areas that are currently using stochastic systems, beings, machines, whatever, language models might be a good fit for those. So, for example, I see a lot of people using AI chatbots or something on their website rather than the traditional human tech support. I think that that's not necessarily a bad place to use them. And the reason is pretty simple. And I'm not saying this is perfect. I'm just saying like this might work. And the reason is that before using the language models, we would have sort of these entry level tech support folks that may not have that much knowledge and are just being thrown in to try to make sure customers don't leave the business or whatever, stop using the product. And so they are going to try to answer questions, but they're also stochastic. They're not the knower of all things. They're likely going to get things wrong. And oftentimes, what matters more in those technical support scenarios is that the person on the company side creates a sense of warmth. I mean, if you look at like the psychological studies, oftentimes it's not even necessarily about do they get the outcome that they wanted, but more do they show deep appreciation or create a sense of like respect for the customer and empathy with their problem. And I think language models, at least prior to like GPT-5, could do this, I think, pretty well. And so cases like that where you're in a largely stochastic environment because humans are stochastic systems, machines, beings, I think that they can be very valuable there. On top of that, I also want to share that there are pieces in almost all software that exists where that stochasticity harnessed in the right way can also be beneficial. So one of the ones that comes to mind right out of the gate for me is the way that Notica would be like the mob generation and be sort of like the item loading. There would be some other things too. There was this one gem that would do this random like buffs to items. Okay, so what do these have to do with language models and stochasticity? The mob generation, the way that I think it would work is you could have, and mobs, for those of you who aren't gamers, is like these are monsters or things that you would fight, NPCs. Uh, it's sort of like the computer AI that you're going to fight against, but they're individual monsters, right? So in Nautica, you could have the mobs load when an area repops at basically like 100% occurrence, or you could vary it. You could say, well, there's like 40% that this mob will load, right? So that's a degree of probability. That's some stochasticity, right? Same thing with the items. So the items that the mobs would have, if they're really powerful items, you want them to, or at least in Nautica, want them to load very infrequently. And to go even further, you would have each individual item could have its own like spawn rate or something like this, repop rate. That's also stochastic in the sense that it's I guess more probabilistic, but you could go even further and you could have potentially in some ways it's sort of the same thing, but I could imagine building it where you give a language model a set of items and say, you stochastically decide which items should be loaded this time. And here's sort of just a general range of things. The way that it works on Nautica right now is I think that you can have two different settings. You can have a set of the likelihood of items loading each time for all items with the same percentage. So let's say it's the 10% rate and it has 5 items. So it looks at the first item, it rolls the dice. If it's within the threshold of loading it, it loads it, then it does the second item, it rolls the dice again. So you could set the 10% for all the items, or you can set it individually. And this can be useful when you have super rare item, but the other ones are maybe not as valuable. So maybe they load more frequently, this type of thing. The same is true with these gems where they're like adding these random buffs. It's also a probabilistic thing, and you may want to have different degrees of sort of variation or color in the way that stochasticity works. So the point is that even in things like Nautica or in Mentor, having stochasticity or non-deterministic behavior can be very, very useful. It just needs to be constrained properly. I would argue, I'm not a big gambler, but I would argue that most of the games in the space of gambling are games of chance, but it's constrained chance. So for example, like and again, I don't gamble, so I don't even know what the rules would be. But let's take something like poker, where are you going to get a good hand? It's not clear. And that part is very stochastic. But what's not stochastic is the cards in the deck. Okay. So this is the point that I'm trying to make, is that even in games of chance, like poker or blackjack or whatever, where you want to have this degree of uncertainty, it's constrained, that you're not applying it everywhere. You're not saying, okay, it's going to be a game of chance. And I mean, maybe this would be interesting to do, but I think people would get really frustrated if you did this. Like, instead of the cards, there being like 52 cards in the deck, what if there were like suddenly 75 or 211? Like, what does that do to the game of poker? Imagine if that was also a probabilistic element of poker or blackjack. I don't know how that would change the game, but I suspect some people that are experts in it have thought about this deeply, and they don't do it for reasons that probably make a lot of sense. So the point is that even in these areas where you want stochasticity, it's often constrained, because the constraints, you want them to be kind of burned in, because those rules are the reason why the game is sort of exciting and people understand. You don't want to necessarily like change the rules in the middle of the game. That's oftentimes considered like super unfair. It's like this idea of moving the goalposts, is that you keep moving the goalposts like that. That's not a fair thing to do. So the takeaway here, and I guess what I'm trying to say, is that the fact that hallucinations are now being properly explained as mathematically inevitable, which I have 1000% agreement of and have had for many years, is actually like music to my ears. The moment that I saw this article, I've been meaning to do this VOD for some time now. I'm like elated on how incredible this is. It's like a huge win for science and technology. We are definitely bringing the hype down. Uh, that does not mean that language models don't have value. But I do think we need to be very careful about how we move forward, and that when we want things that have the potential for hallucinations, or we want things that have stochasticity, we can use language models. But when you need to have perfect precision, like a calculator, uh, like in flying airplanes, and almost anything related to modern day technology, your thermostat, your TV, your computer, the base of the system is largely going to need to be deterministic, and you can use AI systems to achieve that determinism. They just are not going to be language models. And there are many different ways to build machine learning systems that don't use neural networks. And maybe as we go further with GTT, I'll start to get into some of the details on how to build deterministic ML. And yeah, like some of the benefits that I've seen in building them, and then some of the weaknesses, right? And that, yeah, that's like a whole can of worms. And so maybe I'll save that for some future episodes. That's basically all I got for today. I'll drop a link to this article in the comments, as well as this paper, in the event that any of you are interested. And I'd love to hear your thoughts. I'd love to hear what you think this is going to do, in particular to the area of artificial intelligence, both in sort of the academic circles as well as in industry. I have some thoughts. I have some strong thoughts about what it's going to do in academia. I think that part is a little bit more clear to me, largely because I think academics, I think that, or at least a lot of the academics that I work with, they tend to be more based in science and reason. And so I think for them, this is music to their ears. A lot of us were getting like really kind of fed up on every paper that's being submitted to NeurIPS is another language model. It's like, I'm losing my mind. There's more in the world than just this silliness. So I think that in academia, it's going to improve things quite a bit. But in industry, truthfully, I have a certain level of uncertainty. I think that it's very helpful, but I think the there's a lot of marketing, there's a lot of hype, there's a lot of pretend that happens. And so it's not like the world of science, where the scientific, where the system that you're building is accepted based on the merits of the system. In industry, sometimes you can have systems that are really not that wonderful, but they're marketed very well, and so they get a ton of attention. On the other hand, you can have systems that are phenomenally like powerful and great and useful, and they don't make a huge splash for a variety of reasons. And some of them are like very mercenary because they're going to potentially displace a big player, and then bad things can ensue. So I'd love to hear what all of your thoughts are. Feel free to drop some stuff in the comments, and I hope that we all learned something useful. I think that this is definitely making me more optimistic every day. Thanks, everybody.